Hello and welcome to Tektronix web seminar. Today I'm going to present Tektronix TekExpress for 10 gigabit KR application. I will be using a DPO73304DX oscilloscope, which is available with bandwidth up to 33 GHz with 100 gigasamples per second on 2 channels, or 23 GHz with a sampling rate of 50 gigasamples on 4 channels. Together with that oscilloscope and as a DUT, I will be using an AWG 70001B, which offers up to 20 gigahertz of bandwidth and a sampling rate completely adjustable up to 50 gigasamples per second. On that AWG, I took the liberty to prepare a library of test signal that will be available for you as a setup file for 10 giga KR. And opening that file, you will find different test signal as following, as per the IEEE 802.3 standard. You will find PRBS sequence at 10.3125 gigabit per second. You will find a 1010 clock signal. You will have N1, N0 sequence, which is in this case a sequence of 10 ones followed by a sequence of 10 zeros. And then you will have the 6 configuration for the 3 different cursors pre-distortion. We can call that pre-emphasis or de-emphasis settings, C0, C-1, and C1 as per the IEEE specification for 10 gigabit KR physical layer. So let's start with the PRBS sequence. I will drag and drop the PRBS sequence here, and I will generate that inside the AWG. So I'm running and I press enable channel, and let's switch to the scope. So now, as you can see, I have a waveform here. I can make a quick analysis. If I didn't purchase the TekExpress solution for 10 gigabit KR, I can use the standard tools. And when you purchase nowadays DPO73304DX oscilloscope, you will get DPOJET Advanced inside. So let's say that signal is connected from the AWG to the scope using channel 1 and channel 3. So I will say, okay, I would like to analyze channel 1 minus channel 3. Okay, then I will switch off channel 1. I'm just interested in the differential mode, and to make your life simple, you just need to go to the Analyze menu, you go down to DPOJET, and you enable the one-touch jitter wizard. That will basically do all the hard work for you, assessing the amplitude in fast-tack mode of channel 1 and channel 3, and setting up the vertical sensitivity of the oscilloscope. So you will be using 90% of the grid to capture the signal, and thus you will get the best signal-to-noise ratio to quantify the signal for further analysis. So once the vertical scaling is complete on channel 1 and channel 3, they will be turned off, and there will be only the math one remaining, and the oscilloscope will acquire a deep memory of that differential signal. It will put in place a software clock data recovery and detect the data rate, which is the correct one here. It will also detect the pattern length of the PRBS. I'm not totally conformant to the standard here because I'm using a 511 UI pattern, which is a PRBS 9, I guess, as I didn't have the PRBS 11 requested by the standard. So when that algorithm DPOJET has figured out the data rate and the pattern length, is doing a clock recovery, so is rebuilding a clock emulating a PLL based on the edge detection of the signal, and is plotting the eye diagram thanks to that recovered clock. The second thing is doing with the clock recovery is is computing the TIE plot. The TIE, or time interval error, is the fancy name on scope for jitter, and that plot consists of advance or delay values of each of the data edges compared to the clock recovery edges. And that plot now is analyzed through 3 different tools. One is the histogram. So histogram is giving you the raw distribution of your jitter. And we are also making a FFT analysis of the TIE trend. So the TIE trend, or jitter in time, is actually sampled on the data rate. So basically, if your data rate is about 10 gigabit per second, then your FFT will be about 5 gigahertz bandwidth. Here it's a little more because this is 10.3125, so your FFT is going a little farther, and that spectrum here is not the FFT of the signal itself, but of the jitter. So if you have outstanding jitter frequency coming inside the FFT, it will be easy to spot them here. Then the next thing the algorithm is doing is computing the data-dependent jitter. So your pattern is looping into the memory. You have many times 511 UIs looping into the memory, and the algorithm of DPOJET is averaging the bit that goes together. So the first bit with the first bit with the first bit, hundreds or thousands of times, and all of that for the 511 bits from that sequence. And that averaging of the jitter versus pattern allow to get rid of anything which is not correlated with that data pattern, and that gives the data dependent jitter information. And then you will have advanced analysis behind that can be spectrum based or tail fit algorithm, depending of the case, that will be used to extract the random jitter of the component of the jitter and the deterministic jitter, and then that will be used to extrapolate as using the random jitter RMS. The scope DPOJET is going to extrapolate the slope of the bathtub curve here in order to predict the total jitter at predefined BR level. Okay, that's everything you can do with DPOJET. Of course, if you find these measurements that are not complete for you, you can add many more. I will, for instance, add a positive width measurement. You can add many measurements, whether in the period frequency domain or jitter. In the time domain, you will find way more. Of course, the eye diagram measurements and mask test and mask it, and also in the amplitude domain. And you will have additional settings per standard. So you can, as a debug feature, you can purchase DPOJET profiles for specific standard to get the very measurement related to that standard. For instance, for DDR5, you can see here a specific set of measure for DDR5. If you go to PCI Express Gen 4, you will have the measurement for PCI Express Gen 4. So let's be back to the measurement I just added and recompute the memory with that measurement added. Nice features of DPOJET is the capability to debug and pinpoint outliers in specific parameters. So for instance, that is the jitter, and you can easily spot and locate the edge which is the most early and the edge which is the most late in that capture. In the same way, if you want to isolate the narrowest pulse in the data stream, you just have to click to the magnifier next to the smallest pulse, and if you want to see the longest one, you will click on the magnifier on the max value of that. It's very convenient for debug. So let's say now we want to do a TekExpress 10 gigabit KR directly, okay? So let's default everything from 0. You don't need to touch the scope settings in order to proceed on the 10 giga KR application. You just go to Analyze, and then you go to TekExpress 10 gig KR. And there you have the TekExpress GUI open. You can rename the DUT the way you want. You can use live waveforms or replay a pre-recorded waveform setup. And you can acquire the signals either in single-ended, which is my case here. Channel 1 is receiving D plus from the AWG and channel 3 is receiving D minus. Or you can use a differential probe. Of course, if you have multiple lanes, you can also check the different lanes and build a report that will encompass the 4 lanes. In the test selection menu, you will find all the mandatory measurements dictated from the IEEE 802.3 section 72.7.1. And for the purpose of the demo today, we are going to skip some of the tests. This one doesn't make sense because I'm using an AWG, and I will also skip these ones because I haven't developed the waveforms on the AWG to mimic all of that settings, which was too time consuming. So I will add the common mode test, and we will be good to run the application. Just to highlight, for each test, you will get a description here, and when we will run the application, we will have schematics and signal test modification information to follow. So your DUT 10 gigabit KR will need to be set up in the different test mode I mentioned, matching the pattern I've created on the AWG. So let's start with that right now. So the first thing, again, that the 10 gigabit KR TekExpress application is going to do is to do an autoscale of the signal. So first, the application is asking you to connect your DUT to the scope channel 1 and channel 3 through the DC blocks. DC blocks is there to protect the scope and to remove the bias DC component coming out of the DUT. In my case, I don't have the DC block because I'm using a AWG, so there is no common mode bias on the signal. So I will just enable the AWG that I will show you right away, and I will press OK with the PRBS sequence coming out of the AWG. So now you can see the auto scaling of the vertical sensitivity of the channel 1 and channel 3. You have the differential math coming up, and I've set up the oscilloscope to acquire 5 times each measurement, so we can have some statistics running on that. So now he wants the 1-0 pattern, so I will select the 1-0 clock pattern on the AWG, and I will press OK. And again, is performing the auto scaling, because you can of course enable each test independently, and so it will work in this case as well. Now the application expects the N1 N0 pattern, which is a sequence of n bits at 1 and n bits at 0, and in my case I'm using a sequence of 10 bits of each inside the AWG, and now I'm outputting the default value N1 and 0 in terms of amplitude and pre-distortion. So after you will acquire again 5 waveforms, I'm going to go back to the PRBS sequence for the sake of the jitter decomposition analysis. So it's going to run the capture of the PRBS sequence for the jitter decomposition. And again, saving 5 waveforms for that purpose. So now we are expecting to analyze that cursors, pre-emphasis, de-emphasis settings. So we've been acquiring so far. We will get the reference waveform with the one with default configuration. And subsequently, we will acquire the C0, C-1, and C1 increment or decrement settings waveforms, and afterwards the application running will proceed to compute the measurement and the margins. Now we are expected to switch to the C1 increment settings on the DUT. So I will select 10 gigas C1 increment on the AWG and press OK. Now the application expects the C1 decrement settings, so I will select the C1 decrement setting and press OK. All the while I can show you on the AWG what the waveform looks like. So now we want the C0 increment waveforms. So let's go to C0 increment and press OK. You have to take into account that some of the peaking on the AWG is there for a purpose, which is to counterbalance the insertion loss of the cables down to the oscilloscope here. So now we need the C0 decrement. So C0 decrement and OK. And the last one will be the C-1 increment and C-1 decrement. So C-1 increment, I don't want to make a mistake here. And OK. And C-1 decrement. And OK. Okay, last measurement is that I think it's the common mode voltage limit, and that will be done again on the PRBS sequence. So let's switch to the scope screen alone, so we can better see what's going on. So the TekExpress application has finished the acquisition campaign of the waveform and is now processing the waveforms for all the tests required. And so that will take a few tenths of seconds because I used a 5 times iteration capture from a setting before running actually the application, so I can get some statistical effects and see the results of that. So now the application is reloading the PRBS sequence and is computing the jitter decomposition for RG, DG, and TJ bear using the DPOJET application behind. So I can use that time to show you quickly in the AWG. I've been using the emphasis settings plugin. So you have a plugin called High-Speed Serial on the AWG, which allow you to generate any type of pattern, PRBS, or custom clock. You can set up encoding. You can set up encoding scheme with PAM4 or NRZ. And you can also apply scrambling. You can modify the step response or the duty cycle. And I was using the pre-de-emphasis setup here, where you can adjust the cursors. You have five taps on the pre-emphasis, and you have um, also a pre-shoot tab where you can adjust, and I've been using that to generate the waveforms required for the 10 gigabit KR application. We also are proposing optical coherent modulation settings where you can use that together with a optical modulator to do coherent application. We are providing a pulse application as well for specific step generation, either in the baseband domain or in the RF domain. And here is the test report generated by the TekExpress 10 gigabit KR application. As you can see, we started at 5:15 p.m. and the execution time for 5 iterations of each measurement was 12 minutes and 30 seconds, which make a single pass measurement about 2 minutes and 30 seconds. So now let's have a look at the summary here. You will get on the report, of course, the scope identification, serial number, calibration status, the different firmware versions from the main oscilloscope, the DPOJET, and the TekExpress and framework versions as well. So then you get a summary of all the tests that has been passed with the global status. For each test, you can simply click on the title, and you will be brought to the area in the report with the measurement results. So you can see there is the baud rate here, which is pretty stable. The maximum amplitude measured on the first signal, and we have margins up to 1200 millivolts. Then we get the rise times, which must be between 24 and 47 picosecond. We get the jitter decomposition, and you can compare with the high value that we have plenty of margin. Please note that these are not seconds units. This is percentage of UI. UI is being the bit time, so it's 1 over 10.3125 gigahertz. Then we get assessment of the duty cycle distortion as well, which is a percentage of the bit time UI. Then we get that very complicated measurement on the transmitter output waveform characteristics. And as you will see, many of them are very, very narrow in terms of admissible results. If you go there, for instance, you will see that that specific V1 minus V2 measurement is expressed in millivolt, and the boundaries are between 0 and 5 millivolt. And all the while I run that 5 times the same measurement, you can see that we get in the boundaries of that 5 millivolts the 5 time. So it's pretty accurate and repeatable measurements we get here. So let's keep the tables. You can dig into that if you want later. And now you get to the screenshots of the different analysis of the TekExpress compliance for 10 gigabit KR. So that's the trend of the signaling speed in bit time. It's called period, but that's actually the bit time, and the variance of the bit time over time. So 5 times that analysis, of course. Then we get the bathtub capture and the extrapolation and the measurement down to 10 to the minus 12. And you get the reference N1 and 0 waveform measurement. And then you will get that cursor. So now you can see the influence of that pre-emphasis or de-emphasis when we adjust C1. So C1 increment will look like that. And we have 5 times that. So the blue one is remember the blue one is the original, and the red one is the one modified by the cursor. It's easier, it's most easy to see the influence of the C1 decrement here because of that area here. So you can see C1 decrement is actually adding, we are lowering the amplitude of stable bits and the transitioning bits. So switching from 0 to 1, you get a transition. So the first one that follow a 0 will get a normal amplitude, and then the subsequent bit will get a decreased amplitude. That's what is de-emphasis. And this is the other way around here. We've been increasing the de-emphasis, meaning it goes the other way around. The nominal amplitude is the blue one, and we've been dampening a bit that overshoot by touching again C1 cursor, which is the first cursor after the edge. Okay. So let's switch now to the C0. C0 will touch the main global amplitude of the signals, meaning the middle. And so if you get a C0 increment, you see that the red pulse amplitude is slightly over the blue one. Actually, it must be in the boundary of 0 to 20 millivolt. And you can see it's repeatable over the 5 capture again. And now you get the same effect, but in the opposite direction. So the C0 decrement is reducing the overall amplitude of the pulse here. And the last one we want to check is the C-1. And C-1, as much as C plus 1 was the exit of the edge, the C-1 is the tap which is right before the edge, meaning the last the last one before the 0 will have when we increment that, we increment the de-emphasis, so we actually decrement the amplitude of the last one before the first 0. And if you look at the following rising edge, you have the same effect. The last 0 transmitted before the first one will get a slightly higher amplitude. And the purpose of that, again, is to help balance the signal at the receiver, so you get something which is the best possible at the receiver. So the whole purpose of pre-emphasis or de-emphasis distortion is to get the signal better at the receiver side, so to account for the channel. I think that's it for now. I thank you very much for your attention. Please contact Tektronix for more information. My name is Pascal Grison. I'm a field application engineer based in France for Tektronix. Thank you very much and have a good day.